So this is the first session in the series of 10 sessions. We're going to discuss the softwares, we're going to discuss the basics, the theory, and some of the equations. Uh, let's begin. A disclaimer, you might want to change your major to aerospace after this session. So let's start from the very basics. So there are people from non-STEM background too, so I'm going to start with very basics. So what moves a rocket up? Like what moves anything at all? We have to push to move anything, right? And one more request before moving on. Uh, Please don't feel ashamed in asking any questions and ask as many questions as possible because that's gonna make the sessions more engaging and more fun. And feel free to stop me at any point if you don't understand anything. Now, let's describe a little bit more that what moves anything at all. Now, if this astronaut would try to push, can he move? No, he cannot, right? Or look at this guy. He's trying his best to move himself, but he cannot because there's nothing to. They don't have anything to push against. So the word push is incomplete. So the complete phrase should be push against what? So push against the complete phrase. Only that makes sense, right? For now for an aircraft, what can an aircraft push against? What's up in the air? It's just the air. So for example, this helicopter, it it's pushing the air with its propellers, and that's why it's going up. Now, how to push in a way to move huge objects and pretty fast. So, like to increase the speed, we need to push things faster and push more things. So faster and more stuff. And what will that look like? Like a Boeing 737? Not really. So now there's a difference between air propulsion and propulsion in space. So in space we don't have even the air. So what can we push against? So let's define the push a little bit more. What do we get if we push something? We get something called momentum. We denote that by P, and its formula is mass times velocity. We describe a physical quantity uh, by multiplying the mass of the object by the velocity of the object. And the thing that we push against gets the same momentum, but in the opposite direction. So it's a vector. But outside the Earth's atmosphere, there's no air to push against. So we have to figure something else out, right? Propel in space. Now, before moving ahead, I want to clear some of the terms that we're going to require. So the first term is the Mach number. Uh, so imagine that an object is moving at a velocity v through some fluid, through some fluid medium, and if and we describe a quantity called Mach number for that object, and we also describe Mach number for fluid itself. So it's kind of confusing if you look at it, but the air also moves by being disturbed from that object. So we describe Mach number for the object as well as for the air. So the Mach number for air molecules is going to be described like this: the speed of the fluid with respect to the rest of the medium divided by the speed of propagation of pressure waves in that medium. So if you throw a stone in a pond, let's say, so you're going to see some waves that'll emerge from the point where you threw the stone, and they'll propagate further. And the speed of their propagation is fixed. So similar is the case with pressure waves in air. So in air, when anything disturbs the air, the pressure waves, that is the sound waves, moves with a certain speed. If you're going to divide that speed, I mean, if you're going to divide the speed of the object with that speed, the propagation speed of the pressure waves, then you get the Mach number for that object. Now that object could be the air itself, and the object could be something like an aircraft. So we denote the speed of propagation by c, and we denote the speed of the medium or speed of the object by v. So uh, if you want to see how pressure wave looks like in air, or pressure waves, I mean the sound. The sound is nothing but just pressure waves. So imagine if you hit some tweezers or tongue like that, it's going to make a certain frequency of sound. So this sound is going to move ahead by compression and rarefaction of the air molecules, and those waves are going to look like this. They're traveling from left to right. The part which looks like more black is the pressure, is the part where the pressure is in peak, that is the highest pressure, and the one that looks very unpopulated, like wide areas, they are the crests of the pressure wave. But life is not so simple, right? Now, what if your object is moving greater than these waves, at a speed greater than these waves? So things become tricky from here. So if imagine if v surpasses the c, so this fraction is gonna be more than one, the greater than one. So in fluids, now say for example, imagine a jet plane moving through fluid at a pretty high speed, but less than Mach 1. So it's going to disturb different air molecules differently. So at the very nose of it, the all of the molecules are going to get velocities uh, twice of that of the aircraft, and not exactly twice, but a little higher than that. And at the wings, for example, the the molecules are going to get a velocity that is going to be different. So basically, my point here is that a complicated shaped object moves and disturbs the molecules differently at different paths. So even when let's say your object is traveling at Mach 0.8, some of the air molecules could be traveling at speeds greater than Mach 1. So, and if the air travels greater than the speed of the propagation of waves itself, then something really interesting happens. It's called sonic boom. It creates shock waves, and uh, those are basically multiple pressure waves stacked on top of each other, uh, which are like the troughs and crests of these pressure waves aligns with each other, and they basically multiplies. And the speed of sound depends on other factors of the medium. If you do the basic calculations, while you have these calculations, you're gonna see that um, the speed of you can derive the formula for speed of sound, and that formula is gonna look like this for ideal gases. Now this k here is the gas constant, and this gamma is this is the ratio of specific heat at constant volume with specific heat at constant pressure, and you can use this formula for getting to that gamma factor for the gases. Now it depends on the degrees of freedom of your gas molecules, and by degree of freedom I mean in how many ways, in how many vibrational or translation ways the energy in your gas could be distributed. For example, there could be three motions, one along the x-axis, one along the y-axis, and one along the z-axis. and there could be three rotational degrees of freedom. One rotation along the x-axis, one rotation along the y-axis, and one rotation along the z-axis. And then there are vibration degrees of freedoms as well. They look kind of like this. And if you're gonna solve this, for example, oxygen molecule, which is a diatomic molecule, you're gonna see that it has no significant vibrational mode, but it has two significant rotational modes along y-axis and along z-axis, but not along x-axis. And the three translation degrees of freedoms. So the total are 5, and you can calculate using this formula that what's the gamma for oxygen molecule. Now, behavior of fluids at different Mach numbers. So imagine a cross section of a wing of an aircraft. If that is moving through the fluid at a speed smaller than Mach 0.8, then we call that subsonic flow, or we call that speed as subsonic speeds. And the fluid behaves not very, like nothing very interesting happens at this speeds. The flow basically splits up from here, and it merges itself back from here. But if your object is moving at a speed between 0.8 Mach and Mach 0.0, Mach 0.8 and Mach 1, something really interesting happens. So this design is called an airfoil design. The speed of fluid traveling above the airfoil travels actually greater than the speed of the aircraft itself. So even if your aircraft is traveling at let's say Mach 0.9, it could be possible that the air above that airfoil design could be traveling at speeds greater than Mach 1. And we can see this phenomena uh, if you're going to test this in a wind tunnel, or even when you see this the vapor cloud around jets when they go from subsonic to transonic. You see this vapor cloud. What happens that creates this vapor cloud is the upper layer of the fluids travels faster than C, and the vapor condenses due to the sudden expansion in pressure, increase in pressure, and hence vapor pressure that momentarily condenses the vapors. Now, uh, now I have pasted these slides for Mach between Mach 1 and Mach 1.2, and and beyond Mach 1. So we basically classify different speed regimes as subsonic, transonic, then supersonic, and then hypersonic flows. So speeds greater than Mach 5 are hypersonic. Speeds between 1.2 Mach and 5 are called supersonic, and below that, transonic and subsonic. So we like once we cross this Mach 1, something interesting happens. As I told, the shock waves. Now there are two types of shock waves: the compression waves and the expansion waves. Now, compression waves occur mostly at the front face, that is the part that pierces through the fluid, the first, and expansion waves happen at the, for example, this trailing edge of the airfoil design. Uh, and that happens because in the regions where pressure is, where there is the high pressured flow mixes with the low pressured flow, uh, this expansion waves happen. The air suddenly expands. Now, for curious people, they can go and study how bow shocks work, oblique shocks, and the theta versus alpha curve. So this angle theta of the nose cone decides that what's going to be the angle of the shock wave This is called oblique shock, and this is called bow shock. You can study the relation between this angle and the angle of the shock wave. Now, okay, all that is fine, but how would I know that how much fuel do I need to burn? I guess let's do these slides later, a bit later. So we were talking about what to do in space, right? We can carry something with us, then we can push against that. Now, in space, there's no air, there's nothing we can push against. But we have to carry our own stuff that we will push against if we want to propel. Now, if we took enough of it and also we push it fast enough, then we will be able to propel our spacecraft. We can't do that manually, unfortunately, but we need something else like uh, something automated. We call those engines. What could that be actually? So the first thought that came to my mind is, what about utilizing the energy stored in the chemical bonds? Now, if you're gonna react certain reactants that are not much stable, but the products that they create are very stable, then you're gonna see a certain release of energy, and that energy is gonna be converted into the kinetic energy of the gases. So you can basically push those gases really fast. Or how about having some charged ions and then propelling them using electromagnetic fields? Or how about radiation pressure from the sun's radiation, or creating radiations by itself? So we have a lot of options, but the most powerful option is the classical combustion rocket engines that utilizes the chemical reactions. Now let's see what fuel options we have. What reactants can we actually react together to get that chemical energy? So generally, they involve hydrocarbons and some oxidizers in the reactants. Then they combine and create carbon dioxide and water and heat energy. Now, we could use some of the monopropellant like hydrogen peroxide and some catalysts like silver or uh, platinum. So, what a catalyst basically makes it react, makes it decompose. In this case, hydrogen peroxide will decompose into oxygen molecule and a water molecule, and that's more stable than the hydrogen peroxide that we started with. So there's a release of energy in that reaction. And similarly, we have many other options, honestly. Now, but if what if we don't want to use a monopropellant and catalyst? So we can go on to the bipropellant and we can ignite those two propellants together. Like we're gonna mix fuel and we're gonna mix oxidizer together and then we are gonna ignite them. So we can use liquid oxygen with kerosene. Um, Aerospace grade kerosene is called RP1. Or we could use nitric acid or unsymmetrical dimethyl hydrazine, inhibited red fuming nitric acid with again unsymmetrical dimethyl hydrazine. Or what if we want to use a different fuel and a different oxidizer, but we don't want to ignite them? Because what if our igniter failed in some mission? So for being more reliable, we can use such fuels that you don't even need to ignite them. You just combine them, you just mix them, and they ignite by themselves. So such fuels are called hypergolic mixtures. For that, you can use nitrogen tetroxide and hydrazine, and there are other options as well. So these are basically the major options that you have that you can use as propellants. Up until here, does anyone have any questions? Or you want me to discuss some point further? In propellants.
I came in. I came in a little bit later. So initially, you were talking about like Mach speeds and like the shapes of uh, like how different objects interact with the air, right?
Yes. Okay.
So I'm just trying to see like
Gotcha. So we talked about that how complicated shaped objects could um, could give different speeds. Like they can disturb air molecules differently. For example, air molecules that are gonna be hit by a wing of the aircraft could move at different speeds than the nose cone of the aircraft. So we talked about uh, we studied those interactions with the help of this airfoil. We study the that how this airfoil affects the the fluid medium around it at different speeds. So we talked about subsonic flow, transonic flows, and then supersonic and hypersonic flows. So we said that at speeds below Mach 0.8, it's called subsonic flow. The flow just moves above, like the flow splits from here uh, and then moves above a little bit faster from above the airfoil and a little bit slower from below the airfoil, and that creates the pressure difference, which actually lifts the aircraft. But as soon as the speed increases from subsonic to transonic, that is less than Mach 1 but greater than Mach point 0.8, the the flow above the airfoil could actually reach speeds greater than Mach 1, and in fact below as well. So if the fluid particles are moving at speeds greater than Mach 1 here, so they are going to stagnate on top of each other because they cannot move faster than the uh, like the particles ahead of the. So I'll give you an interesting and easy explanation. Now imagine a grid of particles. Now there's a certain speed that the disturbance could flow in this. The disturbance cannot flow at a speed greater than this. Now if you disturb these particles from here, but the air molecules are actually moving faster than the disturbance itself, they're going to stagnate on top of each other. Right here, they're not stagnating on top of each other. But so imagine particles stagnating on top of each other here. So the pressure in this region is going to increase, which is going to increase the vapor pressure, which actually causes the condensation, like the momentarily condensation that we see here at the Mach cone created by a fighter jet. So, and I said that if you are curious and want to study further, you can study bow shocks. Bow shocks are these, and oblique shocks, and theta versus alpha curve. So we and we also studied that once this happens, this creates shock waves. When the fluid particles moves greater than the speed of this propagation of pressure waves, it creates shock waves, and those the nature of those shock waves could differ. So, for example, we have compression waves and expansion waves. Compression waves occurs at the nose of the object that is moving, and expansion waves occurs at the trailing edge. And then we said that these could be further the compression waves could be further divided into two. That is the bow shock, this one, and then this oblique shock. Let me show you the picture of a bow shock. So can you see the shockwave generated by this, the heat shield of the Mars lander? So
Oh,
here,
yeah, I can see.
yeah, here they have a very blunt shape. So the only possible shockwave here is the bow shock, because you need a pointy edge in order for oblique shocks to be created. Otherwise, and there's not much difference between bow shocks and oblique shocks. The only difference is that bow shock is actually detached from the object itself. There's a distance between the shock wave and the object itself. But in oblique shock, the shock wave is actually attached to the object. So in heat shields, we want the shock wave to be detached. Otherwise, it's gonna eat the heat shield. It's gonna destroy the heat shield completely. So that's why we use a very blunt shape. And if that's not a concern for you and you want higher speeds, then you can go on to the pointy shape. But even then, you would not want your shock wave to compress at a to compress more than a particular angle. You want it to be at a certain distance from the rest of your aircraft. So you can study this angle, the relation of this theta angle and the shock wave angle. If you're gonna just quick search this, you're gonna see this curve. You can study the nature of different shock regimes by this graph. Do you have any other questions?
Oh, sorry, just to see this. Will this slideshow be posted on the Discord? I'm just curious.
Yeah, yeah, I'm gonna post these.
Okay, thank you.
You're welcome. Okay, so let's go ahead. Now we're talking about throwing stuff fast and throwing more of the stuff. So let's increase the stuff. Let's increase the velocity of the stuff that we are throwing step by step. Now we all know that fluid at a higher pressure region flows towards fluid at the lower pressure region. So, for example, in this balloon, the pressure of the air is higher than outside, so the air moves from inside to outside, which propels the balloon forward. Similarly, what if we fill those chemicals, those reactants that we were talking about just now, in a high pressure tank and let it flow backwards? So that's going to propel our aircraft or spacecraft forward, right? So it's going to look something like this. And because this is high pressure, it's going to flow out from here and it's going to propel our aircraft forward. Now, but that's not fast enough. That's fast, but that's not fast enough. Now, what if we want to increase the exit velocity even further? So we can ignite those fuel just before the exit so that they expand further. And if they're going to expand further, they're going to they're going to go out with more speed because the volume is increasing in this section. This is basically chemical energy being converted into kinetic energy in action. Now, if in this case the pressure is let's say double of this, so the exit velocity is going to increase. But there's a trade-off between how much pressure you want your tank to be at, because if you're going to increase the pressure too much, your tank is going to blow up. If so, you need a stronger tank for storing a higher pressure gas. So if you are going to make your tank stronger, it's the weight of the tank is going to increase significantly. So see this tank. So there's a trade-off. Beyond a certain point, you cannot increase the thickness of your tank. So now, how to increase the exit velocity further? You can actually, instead of making the entire fuel tank that is huge, really strong, you can add a highly pressurized tank storing a gas like that doesn't even react with this. That doesn't react with the fuel. So and put a valve here, and then you can control that how much pressure do you want your fuel tank to be at just by controlling the valve here. So this is a much better idea in action if you're gonna compare the two. So let's move ahead with this design. Now, you remember that when you shrink the exit of your hose pipe, the water coming out of it comes at a higher velocity. So the converging, so we can use the same convergence at the exit at the nozzle of our rocket as well. So to increase the velocity further. But now I have a question. Can you keep on converging it further and further and further, just like the just like the hose of a water pipe? Can you, or there's gonna be a point beyond which even if you decrease, even if you shrink it more, the velocity doesn't increase.
I think it's when you close the valve completely, right? Where the velocity just, or you're saying like, as you keep closing it, it increases and then it reaches the point where it just stops, right? Because I think that's when you just close it, right?
No, but my question is like, you have very high pressurized gas, you have high pressurized fuel tank, but then can you keep on converging your nozzle more and more to increase the exit velocity further and further? Or there's going to be a point beyond which you, even if you converge your nozzle, the velocity at the exit velocity of the gas is not increasing.
I think there'll be a point where it will stop increasing,
Yeah,
like as it comes.
yeah, you're right. There is such a point. And precisely when your exit velocity reaches Mach 1, and if you converge your nozzle further, then it, instead of increasing the velocity, it decreases the velocity. The reason is pretty
So,
simple. Yeah.
what about in space, though? So, suppose you're not. Suppose you're in some kind of vacuum.
Mhm.
Um, then you don't have a Mach number determined.
Okay. So, uh, but if you're gonna talk about the fluid flowing inside the nozzle itself, it has its own Mach properties, right?
Yes.
Yeah. So the reason is pretty simple. This is the pressure contour. So the pressure on the left is really high, and as we converge the nozzle further, the pressure drops, as you can see. Up until here, the pressure was dropping, but if you have converged this even further, the pressure, instead of decreasing the pressure, you're gonna increase the pressure. Why? Because again, imagine the molecules that are over here. They're moving at a speed greater than the information can travel forward. So they are stagnate on top of each other, and the local pressure is gonna increase instead of decreasing. So if you wanna increase the velocity of your flow, you have to have the pressure decreasing, decreasing, and decreasing. Otherwise, the chemical, the energy that is stored, like the pressure energy and the temperature energy, is not going to convert into the kinetic energy of the gas. So our aim is to make the design of the nozzle in such a way that as you go down, the pressure keeps decreasing. So if you're going to diverge this and allow the stagnated gas, that is uh, molecules moving faster than the information can travel inside a gas. If you're going to give more space to those stagnated molecules, it's going to expand, and instead of increasing the pressure, you're gonna release the pressure. So the pressure is going to decrease if it's going to have more space after Mach 1, and the speed keeps increasing because the temperature keeps dropping. So this is the pressure contour, this is the temperature contour, and you can see this results in increasing velocity. The velocity is increasing all the way. Do you have any questions, or do you want some time to digest this?
So Mach 1 is basically like a constant um, to where like basically like is basically like we all keep track on. Like, does it matter the air pressure? Because like I'm just trying to understand. So like Mach 1, we see these happen in normal Earth's air pressure, right?
Yeah,
Or does it depend on? Oh, okay, okay.
we do see that. And so now you can ask now you can ask another question then. So you can keep on expanding the size of your nozzle, right? After this, so this section is the converging section where you're decreasing the cross sectional area. Now this section is the diverging section where you started to increase the cross sectional area. But now you can ask this question that, so what's the best point? Like, you can just keep on doing that, right? You can just keep on increasing the area further and further and get the gases at higher and further higher velocities. But but as if you're talking about atmospheric pressure, so the best possible expansion could be when the pressure over here at the very end matches the pressure of your atmosphere. This is the best condition for due to a certain reasons. Like if imagine that the atmospheric pressure outside is 1 bar, and the pressure at your exit, like at the exit of your nozzle, is, let's say, 10 bars. So it's much higher than 1 bar. So your exhaust gases are going to expand. Let me show you. Imagine these are your exhaust gases that and the pressure over here is is 10 bars, and the atmospheric pressure is 1 bar. So this is going to make your exhaust gases expand, and some of the velocity component of these gases, that is this one, is going to be wasted in the axial directions and won't help increase the momentum of your rocket in this direction. So we don't want this case. So now let's discuss the case where the exit velocity, I mean the pressure at the exit of your nozzle is, let's say, lower than the atmospheric pressure. Let's say atmospheric pressure is 1 and your pressure is 0.5. Now what's going to happen is your flow will start to separate from your nozzle even before that, because the air will try to enter your rocket nozzle, and this will actually destroy your rocket nozzle from inside, and the flow uh, is going to become turbulent here. That's gonna that's gonna add into the energy losses. So the best possible scenario is to actually match the exit pressure with the atmospheric pressure. In that case, your flow is uh, the most ideal flow. That is neither of these cases. Is basically saying that if this part if your flow detaches from here, why not just cut the rocket nozzle from here? We don't need this part of the rocket nozzle. Makes Does that make sense?
Yeah. You just want your flows to come out in the same direction that you're trying to thrust.
Yeah.
Right.
So we're just trying to reach equilibrium, basically.
Yeah, you can say that. Yeah.
I think for the most part, it should be a general principle that you don't want to have discontinuous things. So, like, you want the state of the surface of the rocket to be pretty much the same as the surrounding environment. Like in most cases, you don't want to have abrupt changes inside and outside if you can help it.
Exactly. Because in most cases, that actually adds in your energy losses. If you The point that you just said. So, any other questions? Now let's talk a little bit about this slide. So how would I know that how much fuel do I need to burn? So imagine a rocket started from 0 meter per second from the ground with mass m0. Now imagine after t seconds, your rocket has a velocity v and mass m. Now after a very small duration of time, that is tt, your m, the mass of your rocket decreased by dm because some of the gas is left, and the velocity increased by dv because of the momentum exchange. Now, if the gas is left with the velocity v naught, just just with the exit velocity of v naught, you can just uh, equate the final and the initial momentum, and then you're gonna get the formula. I guess there's some. Okay, I forgot to paste the pictures after this. I have the derivation of the. Just a second. Can you see this?
Yeah.
So if you're gonna just solve this equation, and then you're gonna integrate this, you're gonna get this this equation right here. So you can estimate the mass the mass of your rocket, and you're gonna get a relation between the final mass and the final velocity. So if you know the delta v of the orbit that you're trying to reach, then you can actually calculate how much mass you're gonna need. Then just subtract the mass from the mass left from the initial mass. You got the mass of the fuel burn. And so as I said, once you know that which orbit you're trying to reach, you just calculate the delta V required for reaching that orbit, and then decide what fuel that you want to use, because that fuel will decide your exit velocity, that is V naught. And then using this formula that I just derived, you can just calculate the mass of the fuel that is required to be burned. Now, this is that formula looks like, and on this graph, I'm showing the delta V versus the percentage fuel mass. So the pink graph is 200. This is the specific impulse. Let's talk about this in a while. But if you're gonna see for low Earth orbit, the if you're gonna try and reach the low Earth orbit with a rocket of specific impulse 200 seconds, you have to have 99.2% of the entire mass of the rocket just fuel. If you're trying to reach the Mars transfer orbit using the same rocket, you have to have 99 point almost 9% of the mass of the rocket just fuel. So this graph basically shows you that how much percent of the mass of your rocket should be fuel in order to reach using certain specific impulse rocket engines. Do you have any questions?
Hey, I have a question about when a rocket leaves the Earth's atmosphere. So is most of the fuel burnt just to get like the momentum, just to get out of the atmosphere, so it can be able to like go to space? For example, like let's say you're trying to go to the moon, right? So they burn out. Obviously, they still need fuel for like when they're landing and things like that. But like, let's say you're burning, let's say like because it's like a round trip. Let's say you're burning like half the fuel to go to the moon. So does that mean that most of that fuel, like most of that half of the fuel, let's just say, is used up when leaving the atmosphere, right?
Yeah.
I'm just trying to see. Oh, okay.
So
Yeah, you can actually look at the blue curve. That'll tell you how much it takes to get you up to low Earth orbit,
Oh, that's
and
interesting. Thank you.
you can see the percentage of your fuel mass that you'll use up. In some sense, like it's not, you have to calculate it, but it gives you some idea. Like 96% of your rocket has to be fuel mass to get you up to like on the light blue curve or something.
All right. Thank you.
so here the two factors that are really important are mass flow rate of your rocket, that how much fuel are you burning per second, and at what velocity the fuel is exiting your nozzle. So if and those two factors decide your specific impulse, that is how much thrust you produce per kg of your fuel burn. So if you are actually producing a really good specific impulse that is 400 seconds, then that means you need less fuel to reach the low Earth orbit. Just take the low Earth orbit just for the example. Now the reason is that if you are producing, say for example, let's take an extreme. Say for example, your rocket weighs 10 kgs and you're producing a thrust of 110 newtons. So your rocket is barely being lifted off. So even if you produce that much thrust for a really long time, you're not gonna reach at much height. But even if the let me show you a graph. Imagine this is your thrust and this is your time axis. So say for example, you have a rocket here. This rocket is producing, the engine of this rocket is producing 1.5 times the weight of the rocket. The rocket weighs W right now. So this is even if you keep the engine on for a very long time and you have this much amount of impulse generated, the performance of this rocket is really poor. On the other hand, if you have a different rocket that produces thrust for a very, let's say, 1/4 of the time that this engine could run, but it produces the same amount of thrust in very little time. So that is going to look something like this. So we prefer this kind of rocket engine because this is going to take the same rocket, for example, W, and say, for example, this produces a thrust of 10 times W. So this is going to take your rocket much higher by producing the same amount of impulse. So that's why we talk about specific impulse rather than just impulse. Do you have any questions in this? The physics is straightforward. Um, just find the acceleration. 9.
What's the G naught in the PowerPoint? There's a constant
You said
in the second formula, the G naught
oh,
in blue.
this is the gravitational acceleration by Earth.
Okay. So is it just in meters per second squared?
Yeah.
Okay.
9.6 something meter per second square. So I guess it's clear. So let's talk about engine cycles. So we call this kind of now we call this setup as a pressure fed engine. But this is one of the many possible types of the rocket engines that you can make. You can have multiple different engine cycles. For example, instead, uh, the only purpose of this highly pressurized gas was to increase the pressure of your fuel tank so that more fuel can be pushed to this combustion chamber in less amount of time. But what if instead of using this pressurized gas chamber, you use a pump that is pumping the fuel from the fuel chamber to the combustion chamber? Let's talk about that. Now, it might be the fastest way to throw stuff out, but such pumps could take like 200,000 horsepowers, and we can't use electric pumps for producing this much amount of power. Like we don't have pumps good enough, or even if we have, then we're gonna need batteries so heavy that it's not gonna be a good idea to put in rockets. Now, if we need a pump and we don't want to use electric motors, so we can use a turbo pump. Basically, it's a pump with a turbine. Now, imagine for a second that instead of directly burning your fuel here and producing the high velocities gases over here, you first burn some amount of your fuel, and with the high speed gases generated over there, you spin your turbine, and that turbine in turn pumps more fuel to your main combustion chamber. So that brings us to gas generator cycle. So you generate some gas beforehand. You take the main fuel into your chamber, into your combustion chamber. So Tim Todd has really amazing videos on this topic. Um, this is the one that we just studied right now. Now, as we talk about different propellant options, we can either use one propellant that was right here, or we could use bipropellant, that is separate oxidizer and separate fuel. Now, in that case, you need two of these highly pressurized tanks. Now, we discussed electric pump fed engines. They're not a good idea. Now, so here we are actually pumping the fuel to this gas generator. Look, can you see my mouse? So the fuel is actually going to this gas generator first, and some of the oxidizer is also going to the gas generator. And this gas generator is, um, uh, with the help of small combustion here, it's generating high velocity gases over here, which spins this turbine, and this turbine then in turn spins these pumps. So this is a turbo pump, and you let these gases exit from here. This is called open cycle or gas generator cycle rocket engine. We discussed pressure fed rocket engines. We discussed gas generator cycle engines. Now let's discuss full flow stage combustion rocket engines. So the combustion, okay, right here. So what if instead of throwing this like show you a video of this actually being ignited. This an actual rocket engine using this. You can see these fumes coming out. Yeah. So look over here. This these fumes are what we just saw. Like the exit, these fumes are those that runs the turbo pump. We just let it go outside. We just leave it in the open cycle rocket engines. But what if instead of just dumping that out, we actually connect this to our main nozzle and mix them, and then like to burn it further, and then let it out. So this brings us to our closed cycle rocket engines. We actually connect this stream to our main combustion engine, main combustion chamber. And so the thing here is like why this open cycle is bad idea. Can you think why is it a bad idea to use this kind of engine? What could be the problem here? I can
You
give
have to,
you a
you have to keep track of both of the fuel tanks, right? That makes sure they're releasing at the same rate. Is that an issue?
but you can control your valves pretty good. Uh, so that's not really an issue. I can give you a hint. The issue is the temperature.
Oh, okay. I see it. The imbalance. Is that for the reaction, or is it just we just don't know how to control the temperature in this case?
So what happens is the like the temperature. If you're gonna combine the fuel and the oxidizer in a stoichiometric ratio, it's gonna produce gases so hot that's gonna literally convert your metal from solid into gases. So
So it's basically like melting the metal. Not really
yeah,
meant to be. Yeah, yeah.
yeah, it's basically eating the metal. So what we do is instead of uh, controlling these walls to make it a stoichiometric ratio, we deviate the ratio of fuel is to oxidizer from the stoichiometric ratio in order to make this reaction cooler, so that our turbine blades could actually survive that. So now there this brings us to two possibilities. It could be either oxidizer rich or it could be either fuel rich. So if it's oxidizer rich, then you have to make your main combustion engine fuel rich, and then attach this stream into that. And if it's fuel rich, then you have to make your this flow here oxidizer rich if you want to join this stream into your main combustion engine. So here is where the complexity starts to arise. Now, so which should be the which should be the better idea? Making this gas generator cycle fuel rich or oxygen rich?
Fuel rich.
Yeah. In most cases, in closed cycle, we make it fuel rich, and but some of the engines are also oxygen rich. See, this is an oxygen rich engine cycle right here. This is oxidizer rich. It's called the pre-burner. Yeah, I forgot the name. It's called the pre-burner. So if you made your pre-burner oxidizer rich, then you have to control these valves in such a way to make it the perfect stoichiometric ratio that you want. And in case of fuel rich, is the same story. Now this brings us to full flow stage combustion engines. I wanted to keep this engine for us for a separate session because it's time now. We're gonna cover the rest of the topics in tomorrow's session. Different aerodynamic drag properties and how to optimize the shapes for different regimes and max Q throttle. We have to look out for the pressure because your rocket is not made of diamond. It has certain it cannot face pressures beyond a certain point, and you have to cut your throttle. You have to bring down the throttle of your rocket when the pressure is just too much. It's called the max Q. We're gonna study this condition, and we have a lot of topics like astrodynamics, avionics, other subsystems. We're gonna cover these in the next sessions. Now, I would like to get some reviews about this session. I know it was the first session. I'm gonna improve from here. Do you have any comments or questions? I'm gonna share this file to the Discord. I'm gonna share right now. Even simple equations could get us started. Like if you want really high accurate modeling of your systems, then you can include complicated Navier-Stokes equations. But even if you don't use that, you can get like 99 point something percent accuracy in your simulations. There's a person that I know personally, and he said that just by using isentropic equations, he simulated the nozzle, the yes, they actually the person that I talked to, he actually used just the isentropic equations, and he got 99.4% accuracy when he compared his simulations with the rocket propulsion analysis software. That software is paid, so we can also use basic equations. You don't have to bring out the tanks in order to kill an animal. I hope you guys enjoyed the session. I have recorded this session, so I'm going to upload this. If you have any doubts, you can just go back, and I'm sharing this PDF.
Thank you.
You're welcome.
The 3 liquid fuel main engines soon will throttle back to 72% of rated performance down in the pocket, reducing the stress on the shuttle as it goes transonic.